Hi, I'm Gokalp, and in this video I'll walk you through the design, the training, and deployment of my oxygen sensing model using physics-informed neural networks. I'll skip the photophysics background and focus on the methods, results, and implementation. My goal was to estimate transcutaneous partial pressure of oxygen from three inputs: the luminescence lifetime, temperature, and pulse count. I explored five architectures, but three most relevant were Architecture 1, which was a physics-only based model. Here, a network predicts star-normal parameters, tau 0, and log KSV using temperature and pulse count. These are plugged into the Stern-Waller equation to compute PO2. It's interpretable and stable, but it's a bit limited in flexibility, and it starts to break down after a certain point of oxygen. In architecture 2, I had a joint training approach. I trained both the physical model and a separate MLP PO2 regressor at the same time, but the gradients interfere at the beginning of the training, and it's a bit hard to ensure that both models stay consistent with each other. In architecture 3, I used a two-stage approach, which I ultimately selected for deployment. First, I train a physics model G5 to estimate tau 0 and log KSV using real data. And then I freeze it, and after that I train a separate regressor F data to predict PO2 from the observed lifetime, temperature, and pulse count, while I add a physics consistency loss to align it with the predictions of G5. And the final network F data was a 5-layer MLP with dimensions 3 for the input, 128 for the first layer, 64, 32, 16, and 1 for the rest of the layers, and the final layer just predicts the PO2. And the physics network G5 is a smaller 4-layer network with 2 inputs and 3 outputs. So I trained the physics model G5 using real measurement data and the analytical form of the Stern-Waller equation with an added offset. There was no synthetic data involved at any stage of training, but you might see that in the code base, but I didn't use any of it in the final model. And optionally, I tried physics-based priors like monotonicity or Arrhenius behavior to encourage physically meaningful behavior, but these were disabled in the final version because I found that they were hurting the training performance and the network's ability to model the data. So after freezing G5, I trained the regressor F data on the same dataset. I added a physics loss that penalizes deviations between its predictions and the lifetime ratios calculated by G5. This helped constrain the regressor to remain on the physically plausible manifold. And after convergence, I optionally unfreeze G5 at a lower learning rate for joint fine-tuning, maybe in the last 10% of the epochs. So to collect the dataset for training, I use the gas mixing test bench at AK211 with a mass flow controller to control the oxygen concentration. And that gave me the ground truth values for PO2. While doing that, I also recorded the lifetime temperature and pulse count for that specific film from the sensor. Unfortunately, I didn't have control over the temperature precisely. I just relied on the AC at the AK building, and it varied passively between 22 and 28 Celsius. Most of my dataset lies in the 5 and 15% oxygen range, which matches the human physiological band. I only have sparse data beyond 20%, but I found that we actually need like beyond 20% as well to accurately model the physics. This lack of high O2 percentage data and temperature variation limits the model's ability to generalize to extreme conditions. So out of all the models, the two-stage architecture performed the best. Um, and I monitored this with basically by looking at the loss and the Stern-Malmer plots of all the models. And so in the final two-stage architecture model, I disabled Archimedes and monotonicity penalties in the final version because I found that the dynamics in the real world data turn out to be more physically complex than what these models or these loss terms suggested. So figure 6 shows the performance on the test set, and model predicts very well in the 5 to 20% oxygen range, but it seems to be doing relatively well even near the boundaries. In real-world testing, I ran the model on a microcontroller with gas concentrations set by the MFC. The predictions tracked true oxygen levels closely, and they are shown in figure 7. And in figure 8, you can see that the quantized int8 model performs almost identically to the floating point version. So I want to talk about the embedded deployment now. I deployed both models, floating point and quantized, to an STM32WB35 microcontroller. The FP32 version streams one row of weights at a time from the external onboard flash, layer by layer using a scratch buffer. So we reuse the same buffer for activations. The Int8 version uses PyTorch post-training quantization with FPGA backend. All weights, biases, and quantization parameters are stored as binary files and read in chunks during inference, like the FP32 model. And both versions run in about 64 milliseconds with a peak power of around 30 milliwatts per inference. And that works out to be around 1.92 millijoules per inference. And everything is written in C++, and I use FATFS to access the flash and the external onboard and basically stream the parameters in. No operating system is used. And I also want to add as a side note that I haven't had a chance to do pruning.